Welcome, dear listener, to a gentle journey through the quiet corridors of the cosmos. Tonight, we invite you to let your body grow heavy and your thoughts drift softly as we explore the most tender and beautiful mysteries that our universe gently holds. There is nothing here that requires your attention or urgency, only soft, slow words drifting like starlight through a dark and peaceful sky. So settle in, close your eyes if you wish, and allow these whispered wonders of the universe to carry you slowly toward a deep and restful sleep. The mystery of dark matter. Somewhere within the vast, silent architecture of the universe, there exists a substance that scientists have named dark matter. A quiet, invisible presence that makes up approximately 27% of everything that exists, and yet has never been directly seen or touched by any instrument we have ever built. It does not emit light, it does not reflect light, and it does not absorb light, yet its gravitational presence shapes the slow, graceful rotation of entire galaxies as they drift through space. Scientists detect its existence only by watching the gentle way it bends and influences the movement of stars and light around it, like the soft impression left in a cushion by something that has quietly rested there. The true nature of dark matter remains one of the deepest and most serene open questions in all of science. The expanding universe. In the 1920s, astronomer Edwin Hubble observed something quietly extraordinary, that the distant galaxies scattered across the sky were not standing still, but were in fact slowly, steadily drifting away from one another, like embers floating gently apart on a slow, dark river. Today, scientists understand that the universe itself is expanding, stretching outward in all directions like the surface of a balloon being softly inflated, and that this expansion is actually accelerating with each passing era of cosmic time. What remains deeply mysterious is the invisible force believed to be driving this acceleration, a presence scientists have named dark energy, which appears to make up roughly 68% of the total energy content of the universe. No one yet knows what dark energy truly is, and it sits quietly at the center of modern cosmology like a gentle, unanswered question drifting through the night. The flatness of the universe. When cosmologists carefully measure the large-scale geometry of the universe, tracing the paths of ancient light across billions of light years, what they discover is something quietly astonishing, that the universe appears to be almost perfectly flat, like a vast, smooth sheet of space stretching outward in every direction without any measurable curve. This flatness requires an extraordinarily precise balance of matter and energy in the cosmos, a balance so delicate that even the tiniest deviation early in the universe's history would have sent everything curving inward or outward into something unrecognizable. How the universe came to rest in this state of such perfect, elegant balance remains an open and deeply beautiful mystery. Scientists suspect that a process called cosmic inflation in the earliest moments of time may have smoothed the universe into its current placid flatness, though the details of that ancient, quiet reshaping remain tenderly unknown. What triggered the Big Bang? The universe we inhabit is thought to have begun approximately 13.8 billion years ago in an event of tremendous expansion known as the Big Bang, a moment when all of space, time, matter, and energy emerged together from a state of extraordinary compression and began their long, unhurried unfolding. Yet what remains one of the most quietly profound mysteries in all of science is what existed before this moment, or indeed whether the concept of before even carries any meaning when time itself had not yet been born. Some theoretical frameworks gently suggest the possibility of other universes, or of a cyclical cosmos that breathes in and out across immense stretches of time, but none of these ideas has yet been confirmed by observation. The true origin of everything remains cloaked in the deepest and most peaceful kind of mystery, drifting just beyond the reach of our finest instruments and most careful thinking. The silence of the universe, Fermi's paradox. Given the almost incomprehensibly vast number of stars and planets scattered across the observable universe, estimated at somewhere around 2 trillion galaxies, each containing hundreds of billions of stars, many scientists quietly wonder why we have never detected any clear signal or sign of another intelligent civilization anywhere in the cosmos. This gentle puzzle is known as the Fermi paradox, named after the physicist Enrico Fermi, who once asked simply and softly, if intelligent life is likely to exist elsewhere, then where is everybody? The universe is so ancient and so enormous that even civilizations far less advanced than our own would theoretically have had time to spread signals or structures across vast distances of space. Whether the silence is because we are rare, or because we are not yet listening in the right way, remains one of the most tenderly open questions of our age. The nature of time. Time flows around us constantly, carrying us gently from one moment to the next in a steady, unhurried stream, And yet when physicists look closely at the fundamental laws of nature, they find something quietly surprising, that almost all of those laws work equally well whether time moves forward or backward. The deep reason why time has a direction, why yesterday always lies behind us and tomorrow always ahead, is something that is not yet fully understood, and it sits at the heart of physics as one of its most softly mysterious open questions. Some scientists believe the forward flow of time is connected to the concept of entropy, the universe's slow, inevitable drift toward greater disorder. But why the universe began in such a state of orderly concentration in the first place remains beautifully unclear. Time, that most intimate and constant of all companions, remains in many ways a profound and peaceful mystery. The black hole information paradox. Black holes are among the most quietly extraordinary structures in the known universe, regions of space where gravity has grown so immensely strong that not even light can drift free of their gentle, inescapable pull. One of the deepest mysteries surrounding them is something physicists call the information paradox, the puzzle of what happens to all the information encoded in matter and light that falls into a black hole and disappears beyond its smooth, curved horizon. According to the laws of quantum mechanics, information can never truly be destroyed, and yet classical descriptions of black holes seem to suggest that it simply vanishes, like a thought dissolving into a dreamless sleep. The great physicist Stephen Hawking spent much of his later years quietly wrestling with this beautiful problem, and though progress has been made, the full resolution of the paradox remains one of the most serene and captivating unsolved questions in all of theoretical physics. The matter-antimatter asymmetry. When the universe was born in its earliest, most brilliant moments, the fundamental laws of physics suggest that equal amounts of matter and antimatter should have been created, twin substances that are perfect mirror images of each other, and that annihilate one another in a soft, silent flash of energy when they meet. Yet the universe we inhabit today is composed almost entirely of matter, with only the faintest traces of antimatter drifting here and there in the cosmos, which means that somehow, in those first ancient moments, a very slight imbalance arose. Roughly one extra particle of matter for every billion matter-antimatter pairs. That tiny, quiet surplus of matter is the reason everything we see, every star and planet and drifting cloud of gas, came to exist at all. Why the universe chose matter over antimatter, and how that gentle tilting happened, remains one of the most tenderly beautiful mysteries of modern physics. The cosmic microwave background. If you were somehow able to tune a radio receiver to precisely the right frequency and listen to the sky in every direction at once, you would hear a soft, gentle hiss of ancient light. The cosmic microwave background radiation, a faint whisper of warmth that fills all of space and represents the afterglow of the universe's earliest era, from a time roughly 380,000 years after the Big Bang. This delicate radiation has been traveling across the cosmos ever since that ancient dawn, cooling and stretching as the universe expanded around it, until it now glows at a temperature of just 2.7 degrees above absolute zero, the very lowest possible temperature, as cold and still as anything in nature can be. Tiny variations in this background glow, ripples of slightly warmer and cooler regions, contain encoded within them the story of how the first structures in the universe formed. And yet scientists are still gently unfolding all the secrets held within those ancient whispers of warmth. The mystery of quantum entanglement. Among the many quietly wonderful phenomena that quantum mechanics has revealed to us, perhaps none is more dreamlike and serene than the phenomenon known as quantum entanglement, in which two particles can become linked in such a way that whatever happens to one of them, no matter how far apart they may drift, is instantly and gently reflected in the behavior of the other. Einstein famously called this quality spooky action at a distance, and he was deeply uncomfortable with it because it seemed to suggest some kind of instantaneous connection stretching across any amount of space. And yet experiments conducted over many decades have consistently confirmed that entanglement is real, that particles do indeed share this quiet, invisible bond across vast distances. What this connection truly means at the deepest level of reality, whether it reflects some hidden structure of spacetime or something even more fundamental, remains a beautifully open question, drifting peacefully at the edge of human understanding. The Pioneer Anomaly. In the 1970s, NASA launched two spacecraft, Pioneer 10 and Pioneer 11, on long, slow journeys outward through the solar system and eventually beyond it into the quiet spaces between the stars. As scientists tracked these spacecraft over the decades, they noticed something gently puzzling. Both probes were drifting ever so slightly off course, as though something was applying a tiny, unexplained force in the direction back toward the sun. For many years, This soft deviation was known as the Pioneer Anomaly and sat as one of the more intriguing unsolved mysteries of spaceflight. It was eventually concluded that the anomaly was likely caused by the gentle pressure of infrared radiation emitted asymmetrically from the spacecraft's own equipment, but the process of its investigation opened many thoughtful conversations about the precision of our understanding of gravity at very large distances. Even solved mysteries, when contemplated slowly, carry with them something quietly profound. The shape of the universe. When we ask what shape the universe has, we are asking a question that reaches far beyond anything we can directly see or measure from our small vantage point within the Milky Way galaxy. The universe could be shaped like an immense, flat sheet stretching outward to infinity in all directions, or it might curve gently back upon itself in the way that the surface of a sphere curves, meaning that a traveler moving in any one direction for long enough would eventually return to their starting point. It might even have a more exotic shape, like the surface of a donut, or some other gentle, complex topology that mathematics allows but our intuition struggle to picture. Current observations suggest the universe is very nearly flat, but whether it extends infinitely or loops back upon itself in some quiet, graceful way remains beautifully uncertain, a question that may never be fully answerable from within. The mystery of consciousness. Among all the unsolved mysteries that science has yet to gently unravel, perhaps none is more intimate and softly profound than the mystery of consciousness, the deep puzzle of how and why subjective experience arises from the physical processes of the brain. Every thought you are having right now, every soft sensation of warmth and rest that you feel as you listen to these words, is somehow produced by the electrochemical dance of neurons firing across the intricate networks of your mind, and yet no one has yet been able to explain precisely how that physical process gives rise to the rich, inner world of feeling and awareness that you experience. This is sometimes called the hard problem of consciousness, and it remains one of the most peaceful and profound open questions at the intersection of neuroscience, physics, and philosophy. The universe, it seems, is not only mysteriously vast, it is also mysteriously deep, reaching inward as far as it reaches outward. Neutron stars and their density. Somewhere in the quieter corners of our galaxy, there exist objects called neutron stars, the dense, compact remnants left behind when massive stars reach the end of their long lives and collapse inward under their own extraordinary gravity. A typical neutron star packs a mass roughly 1.5 times that of our entire Sun into a sphere only about 12 miles across, making it so dense that a single teaspoon of its material would weigh approximately 10 million tons here on Earth. The surface of a neutron star is thought to be covered in a rigid crystalline crust composed of exotic atomic nuclei, beneath which lies a deep interior of compressed neutron matter whose properties remain among the most tenderly uncertain in all of physics. Some theoretical calculations even suggest the possibility of strange quarks or other exotic particles at the very core, resting quietly at pressures our instruments have never been able to directly measure. The axis of evil in the cosmic background. When satellites mapped the cosmic microwave background radiation in fine, quiet detail, scientists discovered something unexpected and gently puzzling, that certain features of this ancient, all-pervading glow seem to be subtly aligned with each other and even, in a dreamlike way, with the plane of our own solar system, as though the cosmos had some preferred direction rather than being perfectly uniform in every orientation. Researchers somewhat playfully called this alignment the axis of evil, a name that belies the serene and mathematical nature of the puzzle, because it seemed to violate the expectation that the universe should look the same in all directions on the largest scales. Whether this alignment is a real cosmological feature, a subtle artifact of how the measurements were taken, or simply a pattern our minds are drawn to find in randomness remains quietly unresolved. The universe, in its vast and gentle complexity, continues to offer patterns that provoke wonder and careful, unhurried thought. The multiverse hypothesis. Some of the most thoughtful and quietly imaginative work in modern theoretical physics has led scientists to consider the possibility that our universe may not be the only one, that beyond the boundary of what we can ever observe, there may stretch an enormous or even infinite collection of other universes, each with its own quiet history, its own laws of physics, and its own soft arrangement of matter and energy. This idea, known broadly as the multiverse hypothesis, arises naturally from several different areas of physics, including the inflationary theory of the early universe and the landscape of solutions and string theory, though it remains deeply controversial because it may never be possible to observe or test. The thought of countless other universes drifting alongside our own, each one vast and complex and filled with its own quiet wonders, is one of the most deeply peaceful and profound ideas that human minds have ever turned over in quiet contemplation. Whether the multiverse is real or a beautiful mathematical abstraction, it gently widens the imagination. The mystery of magnetars. Among the most extraordinarily powerful and quietly awe-inspiring objects in the known universe are a rare class of neutron stars called magnetars, objects whose magnetic fields are so immensely strong that they are estimated to be roughly 1,000 trillion times stronger than the magnetic field of the Earth, a strength so extreme that it strains the imagination to fully picture it. These slowly rotating, compact stellar remnants occasionally release tremendous bursts of energy in events called starquakes, where the rigid crust of the star shifts slightly under the stress of its own magnetic field, sending waves of X-ray and gamma radiation drifting outward through space. One such burst from a magnetar relatively nearby in our galaxy was recorded in 2004 and was so energetic that it gently disturbed Earth's ionosphere from a distance of 50,000 light-years. How these extraordinary magnetic fields are generated and sustained during the formation and life of a neutron star remains an open and quietly fascinating area of astrophysical research. The mystery of fast radio bursts. Astronomers around the world have been quietly captivated for years by an astronomical phenomenon known as fast radio bursts. Intense, fleeting pulses of radio waves that last for only a millisecond or less and yet release as much energy in that brief moment as the sun emits over the course of entire days. These bursts arrive from distant galaxies, many of them billions of light-years away, and most appear to occur only once before fading into silence, though some sources have been observed to repeat in a slow, unpredictable rhythm that has only deepened the mystery. The physical mechanisms that produce them are still not fully understood, with possibilities including magnetars, merging neutron stars, and other exotic astrophysical events being gently explored by researchers. Each new burst detected by radio telescopes adds another soft data point to an accumulating picture that is rich, strange, and beautifully incomplete. The Dark Ages of the Universe. In the long, quiet history of the cosmos, there was an era known to scientists as the Cosmic Dark Ages, a span of hundreds of millions of years following the formation of the first hydrogen atoms, during which the universe was filled with a diffuse, fog-like gas that was neither illuminated by starlight nor warmed by any source of radiation. The universe during this period would have appeared, to any hypothetical observer, as a vast and featureless darkness, cool and still and stretching in all directions without a single point of light to break the gentle, endless shadow. It was only gradually, as gravity slowly gathered that diffuse gas into denser and denser knots, that the first stars began to ignite, small, extraordinarily hot, and blazingly bright objects whose radiation eventually burned away the surrounding fog in a process called reionization. The detailed story of how and when that first light appeared, and what the earliest stars were like, is still being gently pieced together from observations of the ancient, distant universe. The strange smoothness of the CMB. One of the quiet puzzles that cosmologists spent many years pondering is sometimes called the horizon problem, the observation that the cosmic microwave background radiation is remarkably, almost uncannily uniform in temperature across opposite sides of the sky, even though those regions of the early universe would have been so far apart from one another that light could never have traveled between them in the time available. In other words, regions that had no way of ever communicating or exchanging energy somehow arrived at precisely the same temperature, like two people in separate rooms simultaneously reaching for the same object without any signal passing between them. The leading explanation for this gentle smoothness is cosmic inflation, a brief, extraordinarily rapid expansion of space in the universe's first fractions of a second that would have stretched a tiny, uniform patch of space into everything we can observe today. But the precise details of inflation and what drove it remain one of the most peacefully open chapters in the story of the universe. The fate of the universe. When scientists trace the long, slow arc of the universe's future using the laws of physics and cosmology, several different possibilities emerge, each one quietly vast and contemplative in its own way. If dark energy continues to accelerate the expansion of the universe, the distant galaxies will eventually drift so far away that their light will no longer be able to reach us, and the sky will gradually grow darker and more empty over trillions of years. In one theoretical scenario known as the Big Rip, the accelerating expansion could eventually grow strong enough to tear apart galaxies, then solar systems, then planets, and finally even the bonds holding atoms together, in a slow, peaceful dissolution of structure. In other scenarios, the universe may instead cool gradually into a state of maximum entropy known as the heat death, a final, still equilibrium in which nothing moves and nothing changes, like a deep and endless sleep settling over all of creation. The mystery of quasars. In the distant universe, billions of light-years away and therefore also billions of years back in time, there blaze objects of extraordinary luminosity known as quasars, compact regions at the centers of galaxies where supermassive black holes are consuming matter at a tremendous rate and releasing, in the process, more light than entire galaxies containing hundreds of billions of stars. A single quasar can outshine its host galaxy by a factor of 10 or even 100, blazing across the cosmos with a steady, serene intensity that has allowed them to serve as ancient lighthouses for astronomers mapping the large-scale structure of the universe. What remains gently puzzling is how the supermassive black holes at the hearts of the earliest quasars grew so large so quickly, reaching billions of solar masses within only a few hundred million years of the Big Bang. The mechanisms by which these cosmic giants assembled themselves so swiftly in the young universe remain one of the richly textured open questions of modern astrophysics. The mystery of primordial gravitational waves. When the universe underwent the extraordinary burst of expansion known as inflation in its earliest moments, theoretical physicists predict that this process would have generated ripples in the very fabric of spacetime itself, ancient gravitational waves flowing outward from that primordial era and leaving a faint, characteristic imprint in the polarization patterns of the cosmic microwave background radiation. Detecting these primordial gravitational waves would give scientists a direct observational window into the physics of inflation, confirming and elaborating the theory that explains the large-scale smoothness and structure of the universe. However, despite many careful and sophisticated searches by telescopes and satellites positioned in the cold darkness of space, no confirmed detection of these ancient waves has yet been achieved. The soft whisper of that primordial ripple, if it can ever be heard, promises to be one of the most profound scientific discoveries in the history of human knowledge. The mystery of the sun's corona. Our own sun, that warm and familiar presence that rises each morning and fills the sky with its gentle golden light, holds within it a mystery that has quietly puzzled solar physicists for many decades. The surface of the sun, known as the photosphere, has a temperature of approximately 5,500 degrees Celsius, an enormous heat by any earthly standard, and yet the thin outer atmosphere of the sun, called the corona, is heated to temperatures of 1 million degrees Celsius or more, hundreds of times hotter than the surface below it. This seems to violate the intuitive expectation that temperature should decrease as you move farther away from a heat source, and the precise physical mechanism by which the corona is so dramatically heated remains one of the most tenderly unsolved problems in solar science. Leading theories involve wave-like oscillations and small-scale magnetic reconnection events releasing energy into the corona, but the full, detailed picture has not yet settled into clarity. The mystery of cosmic rays. From somewhere deep in the universe, a constant, gentle rain of high-energy particles arrives at Earth's atmosphere every moment of every day, protons and atomic nuclei moving at extraordinary speeds, some of them carrying energy so far beyond what any human-built particle accelerator can produce that their origin and the mechanism of their acceleration remain deeply mysterious. These particles are known as cosmic rays, and while lower-energy cosmic rays are thought to originate from within our galaxy, perhaps from the shockwaves of supernova remnants, the highest-energy cosmic rays appear to come from somewhere beyond the Milky Way entirely, from distant and powerful astrophysical sources that have not yet been definitively identified. They arrive singly and rarely, each one announcing its arrival with a soft cascade of secondary particles blooming downward through the atmosphere like a quiet, invisible flower opening above our heads. Tracing these particles back to their sources and understanding the physics of their acceleration remains one of the quiet frontiers of high-energy astrophysics. The mystery of the Great Attractor. Deep within the fabric of the cosmic large-scale structure, there is a region of space known as the Great Attractor, an enormous concentration of mass located roughly 250 million light-years away in the direction of the constellation Centaurus, toward which our own Milky Way galaxy, along with hundreds of thousands of other galaxies, is slowly and steadily drifting. The gravitational pull of this great mass concentration shapes the motions of entire galaxy clusters across a vast swath of the nearby universe, yet for many years it was difficult to study because it lies directly behind the densely crowded plain of the Milky Way, hidden behind a soft curtain of our own galaxy's stars and dust. In recent decades, observations in radio waves and X-rays have begun to reveal the structures within this region, finding enormous clusters and superclusters of galaxies gathered there. But the full mapping of what lies at the center of this gravitational gathering, and the precise nature of the structures involved, continues to unfold in a slow, deliberate, and deeply beautiful way. The mystery of water in the solar system. Liquid water is one of the most essential and gently remarkable substances in the known universe, the medium in which the chemistry of life as we know it is carried out, and yet its presence in the solar system extends far beyond the familiar blue surface of the Earth, in ways that scientists are still quietly exploring. Saturn's moon Enceladus has been found to have a subsurface ocean of liquid water that gently jets plumes of water vapor and ice crystals out into space through cracks in its icy surface, while Jupiter's moon Europa is believed to harbor an ocean of liquid water beneath a shell of ice that could be larger in volume than all of Earth's oceans combined. How these liquid water reservoirs came to exist and persist beneath the frozen surfaces of these distant moons, and what implications they might hold for the question of life beyond Earth, are questions that rest quietly at the frontier of planetary science. The discovery of water in these unexpected places continues to reshape our understanding of where in the universe conditions hospitable to life might gently arise. The mystery of ball lightning. Among the more quietly perplexing phenomena reported throughout human history, ball lightning occupies a strange and dreamy space at the edge of atmospheric science. Eyewitness accounts describe luminous, spherical objects ranging from the size of a golf ball to a meter or more across, drifting slowly and silently through the air during or after thunderstorms, glowing with soft colors of white, orange, or blue before quietly dissipating or sometimes with a small pop. Despite thousands of reported sightings collected over many centuries, ball lightning has proven remarkably elusive to scientific study, as it leaves no consistent physical trace and has been captured only rarely and partially on video. Numerous theories have been proposed to explain it, including microwave radiation from lightning discharges, plasma phenomena, and electrical interactions with silica particles from soil, but no single explanation has been universally accepted. The phenomenon drifts through the scientific literature with the same quiet enigma it displays in the air, unresolved and gently fascinating. The mystery of the moon's formation. Our moon, that soft silver presence that has watched over the Earth for billions of years and drawn the tides in their gentle rhythms across the ocean's edge, is itself the subject of a mystery that planetary scientists have only partially resolved. The leading theory holds that approximately 4.5 billion years ago, a Mars-sized body known as Theia drifted into a slow-motion collision with the early Earth, and the debris flung outward from that ancient, gradual impact gradually gathered under gravity into the moon we see drifting overhead today. Evidence for this giant impact hypothesis comes from the composition of lunar rocks brought back by Apollo missions, which closely match the chemical signature of Earth's mantle, as well as from computer simulations of the impact's dynamics. However, some aspects of the moon's chemistry and isotopic composition present quiet puzzles that the basic giant impact model does not entirely resolve, and refinements to the theory continue to emerge from careful, patient research. The mystery of Jupiter's Great Red Spot. On the vast, banded face of Jupiter, the largest planet in our solar system, a world so enormous that roughly 1,300 Earths could fit comfortably within its volume, there has persisted for at least 350 years a swirling, oval storm known as the Great Red Spot, a tempest larger than the entire Earth, rotating in a slow and stately counterclockwise motion above the planet's cloud tops. The deep, rusty red coloration of this storm has long been a subject of gentle curiosity among planetary scientists, with studies suggesting that chemical reactions between ammonia and other compounds in Jupiter's upper atmosphere may produce the complex organic molecules responsible for its characteristic hue. What remains puzzling is the source of energy that allows this storm to persist for such an extraordinary length of time, since storms on Earth, even the most powerful ones, dissipate within days or weeks. The Great Red Spot has been slowly shrinking over the decades of observation, from a width of about 40,000 kilometers in the 19th century to roughly 16,000 kilometers today, and what its eventual fate will be remains quietly open. The mystery of the WOW signal. On the evening of August 15, 1977, astronomer Jerry Emmon was reviewing data from the Big Ear radio telescope at Ohio State University when he came across a signal so unusually strong and precisely structured that he circled it in red ink on the printout and wrote the word WOW in the margin beside it. And that simple annotation gave the signal the name by which it has been gently known ever since. The WOW signal displayed all the characteristics that SETI researchers had long theorized an intentional transmission from an extraterrestrial source might possess, arriving from a direction in the constellation Sagittarius at a frequency very close to the theoretically significant 1420 MHz emission frequency of hydrogen. Despite many subsequent attempts to detect it again using the same and other telescopes, the signal has never been heard a second time, leaving it in a peaceful and unresolved state that researchers continue to quietly contemplate. Whether it was a natural astronomical phenomenon, a reflection of terrestrial radio frequency interference, or something altogether more extraordinary remains gently and beautifully unknown. The mystery of the placid rings of Saturn. Saturn's rings are among the most beautiful and quietly spectacular structures in the known solar system. A vast, flat disk of ice and rock particles ranging in size from tiny grains to objects the size of a house, spread across a region some 282,000 kilometers wide and yet, in some places, only about 10 meters thick, gossamer and delicate as a morning layer of frost. What remains puzzling is the age of these rings. Recent measurements by the Cassini spacecraft suggest they may be surprisingly young in cosmic terms, perhaps only 100 to 400 million years old, meaning they formed long after the dinosaurs appeared on Earth. If correct, this would mean they are a relatively recent and perhaps temporary feature of Saturn's appearance, destined to slowly rain down onto the planet's surface over tens of millions of years. The question of where all that pristine ice came from, and what collision or disruption created such a delicate and breathtaking structure so recently in Saturn's long history, is one of the softer ongoing mysteries of planetary science. The mystery of pulsars and their perfect timing. Pulsars are rapidly rotating neutron stars that emit narrow beams of electromagnetic radiation from their magnetic poles, sweeping those beams across space like the soft sweep of a cosmic lighthouse beam, and because of the extraordinary regularity of their rotation, some pulsars are among the most precise natural clocks ever discovered, keeping time with an accuracy that rivals the finest atomic clocks built in human laboratories. This almost unnatural precision arises from the combination of the pulsar's enormous rotational inertia and the fact that it is spinning in the near-perfect vacuum of space, where there is almost nothing to slow it down. Millisecond pulsars, which have been spun up by accreting matter from a companion star, can rotate hundreds of times per second and maintain their rhythm to extraordinary precision across billions of years. Yet occasional, sudden small changes in the rotation rate, called glitches, offer quiet hints about the mysterious internal structure of these dense objects, and the physics deep within a pulsar's core remains one of the most fascinating open questions of neutron star science. The mystery of Titan's hydrocarbon lakes. Saturn's largest moon, Titan, is a world of soft amber haze and thick nitrogen atmosphere that, in some fundamental ways, resembles the early Earth more than any other body in the solar system. And yet instead of liquid water, its surface is dotted with vast, smooth lakes and seas composed of liquid methane and ethane, hydrocarbons that exist as liquids in Titan's frigid temperatures of around -179 degrees Celsius. The Cassini spacecraft spent over a decade gently surveying this extraordinary world, revealing river channels carved by methane rain, vast dune fields of organic sand, and polar seas of liquid hydrocarbons drifting quietly beneath a dim orange sky filtered by layers of organic haze. Scientists have been quietly fascinated by Titan not only for its exotic physical environment but also for the complex organic chemistry occurring in its atmosphere and on its surface, chemistry that, while not the chemistry of life as we know it, may illuminate pathways by which complex molecules can form and accumulate. Whether any form of chemistry that might be called life could occur in Titan's liquid methane lakes is one of the most gently intriguing speculative questions in astrobiology. The mystery of gamma-ray bursts. Gamma-ray bursts are the most energetic electromagnetic events known to occur in the universe, brief, blazing flashes of gamma radiation that arrive from all directions in the sky, originating in distant galaxies billions of light years away, and lasting anywhere from a fraction of a second to several minutes before fading into a softer X-ray afterglow that can be traced for hours or days. In those brief moments, a gamma-ray burst can release more energy than the Sun will emit over its entire 10 billion-year lifetime, a concentration of energy so extraordinary that it is difficult to fully picture with any familiar frame of reference. Long-duration gamma-ray bursts are thought to be associated with the spectacular gravitational collapse of massive stars, while short-duration bursts are believed to arise from the merger of two neutron stars in a slow, final spiral. But the precise details of how the energy is collimated into such narrow, powerful jets remains an area of active and deeply engaging research. These brief flashes from the deep universe arrive as cryptic postcards from events of profound cosmic consequence. The mystery of cosmic voids. When astronomers map the large-scale distribution of galaxies across hundreds of millions of light-years, they reveal a structure of breathtaking complexity, long, gossamer filaments of galaxies and galaxy clusters woven together into a vast cosmic web, and between those filaments, immense regions of near emptiness known as cosmic voids, where almost no galaxies reside and space stretches in quiet, dark solitude for hundreds of millions of light-years in every direction. The largest known void, sometimes called the Boötes void, spans approximately 330 million light-years across and contains only about 60 galaxies where, based on the average density of the universe, one might expect to find around 2,000. How these immense emptiness came to form, exactly how they are bounded, and what the very faint matter within them is doing are questions that continue to be gently explored in the study of large-scale cosmic structure. In a universe full of light and motion, the vast, quiet emptiness of voids carries a meditative beauty all its own. The mystery of exoplanet atmospheres. Beyond our solar system, astronomers have confirmed the existence of more than 5,500 planets orbiting other stars, a number that grows gently with each passing year as detection methods improve and telescope time accumulates. And among the most exciting frontiers of this young science is the study of the atmospheres these distant worlds carry wrapped around themselves as they drift through space. By analyzing the light of a star as a planet passes in front of it, astronomers can detect the subtle fingerprints of molecules in the planet's atmosphere absorbing specific wavelengths, and in this way have begun to build a catalog of what materials drift in the skies of worlds light-years away. The James Webb Space Telescope, drifting at the second Lagrange point a million miles from Earth in cool, dark stillness, has already begun detecting carbon dioxide, water vapor, and other molecules in exoplanet atmospheres with unprecedented detail. Whether the atmospheres of Earth-like planets elsewhere will someday reveal the soft chemical signatures of biological activity, the quiet breath of a living world, is a question that rests at the most profound edge of human curiosity. The mystery of solar wind and space weather. From the surface of the Sun, a constant stream of charged particles, electrons and protons flowing outward in a hot, thin plasma, drifts gently through the solar system in all directions, carrying with it the Sun's magnetic field and sometimes gently buffeting the magnetic envelopes of the planets it passes by. This solar wind, as it is known, interacts with Earth's magnetosphere to produce the soft, luminous curtains of the aurora borealis and aurora australis, shimmering in greens and purples and silvers at the edges of the polar skies. During periods of heightened solar activity, enormous eruptions called coronal mass ejections can send vast, magnetized clouds of plasma drifting outward through the solar system, occasionally disturbing communication satellites and power grids when they brush against the Earth. Predicting these events with the precision needed to protect modern technological infrastructure remains an active area of research, and the deeper physics of how the corona generates and launches these great plasma clouds is still being carefully studied. The mystery of the Oort cloud. Far beyond the orbit of Neptune, past the scattered disk of icy objects where Pluto drifts in its long inclined orbit, there is thought to exist an enormous, spherical shell of icy bodies surrounding the solar system at distances extending from roughly 2,000 to 100,000 astronomical units from the Sun, a vast, cold, and entirely unvisited region known as the Oort cloud. This remote reservoir of cometary nuclei is believed to be the source of the long-period comets that occasionally drift inward through the inner solar system, following highly elongated orbits that carry them close to the Sun before sending them back into the cold darkness for hundreds or thousands of years. Despite being the largest structure in the solar system, the Oort cloud has never been directly observed. Its existence has been inferred from the orbital properties of the comets that visit us, like the memory of a vast, quiet place known only through the occasional visitors it sends forth. Whether the Oort cloud formed in its present location or was assembled from material scattered outward by the gravitational influence of the forming planets is still gently debated. The mystery of Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown published a careful analysis of the orbital properties of a group of distant trans-Neptunian objects, small bodies orbiting the Sun far beyond Neptune, and noted that their orbits appear to be clustered in a way that seems statistically unlikely to be mere coincidence, suggesting the possible gravitational influence of a large, undiscovered planet lurking in the outermost reaches of the solar system. This hypothetical world, tentatively known as Planet 9, would need to be roughly 5 to 10 times the mass of Earth and orbiting at an enormous distance, perhaps 400 to 800 astronomical units, on a long, elliptical path that takes it tens of thousands of years to complete a single orbit around the Sun. Despite extensive searches using some of the world's most powerful telescopes, no direct detection of Planet 9 has yet been made, and its existence remains theoretical, a quiet gravitational presence felt only through the subtle choreography it may be imposing on smaller bodies nearby. Whether it truly exists, or whether the clustering of trans-Neptunian object orbits has another explanation, is one of the most pleasantly open questions currently drifting through observational astronomy. The mystery of the universe's largest structures. As astronomers have mapped the distribution of galaxies across ever larger scales of the observable universe, they have discovered structures so immense that they stretch the limits of our cosmological models, such as the Hercules Corona Borealis Great Wall, a filamentary structure of galaxy clusters spanning an estimated 10 billion light-years across, so vast that light from one end of it takes 10 billion years to reach the other. According to the standard model of cosmology, structures beyond a certain size should not exist, because the universe simply has not had enough time since the Big Bang for gravity to build aggregations on such enormous scales. The existence of these gigantic structures poses a gentle but persistent challenge to cosmological theory, requiring either revisions to the standard model or new explanations for how such filaments and walls came to be assembled. They drift through the fabric of the cosmos like ancient, intricate patterns woven into a tapestry that we are only beginning to comprehend. The mystery of neutron star mergers. When two neutron stars orbit each other in a slow, spiraling dance that grows tighter over millions of years as they lose energy to gravitational waves, they eventually merge in an event of profound consequence. A collision that produces a brief, brilliant flash of gamma-ray radiation, a kilonova glowing with the soft gold and red light of newly forged heavy elements, and a burst of gravitational waves rippling outward through space-time. In 2017, for the first time in history, both the gravitational waves and the light from such a merger were detected simultaneously, allowing scientists to study the same event across multiple cosmic messengers simultaneously, an achievement that marked the dawn of what is called multi-messenger astronomy. Among the most exciting findings was confirmation that such mergers are responsible for forging gold, platinum, and other heavy elements in the periodic table. The gold in every ring and necklace on Earth was born in an ancient, quiet collision of neutron stars somewhere in the early universe. How the conditions in these mergers determine the precise quantities and types of heavy elements produced is still being carefully unfolded. The mystery of rogue planets. Among the more quietly evocative objects that astronomers have begun to catalog in recent years are rogue planets, worlds that drift through the interstellar darkness completely alone, unbound to any star, traveling through the cold between the galaxies on solitary journeys of perhaps billions of years. These wandering worlds are thought to have been ejected from their original solar systems by gravitational interactions with other planets or by the disruptions of close stellar encounters, sent tumbling outward from the warmth of their parent suns into the deep, quiet cold of interstellar space. Current estimates suggest that rogue planets may actually be more numerous than stars in our galaxy, meaning the cold, dark, planet-dominated spaces between the stars may be full of these silent wanderers drifting by in complete isolation. Whether any of them could sustain liquid water beneath a thick atmosphere or in a subsurface ocean warmed by internal radioactive heat, and whether any form of life could endure on such a world of perpetual darkness, are questions that drift quietly at the edge of scientific imagination. The mystery of why the universe has three spatial dimensions. Among the quieter but most philosophically profound mysteries in theoretical physics is the question of why the universe we inhabit appears to have exactly three dimensions of space: length, width, and depth, when the mathematical frameworks we use to describe nature at its deepest level are not especially constrained to this number, and string theory in particular suggests the possibility of 6 or 7 additional spatial dimensions curled up at scales too tiny to detect. One line of thinking holds that 3 spatial dimensions may be uniquely suited to certain features that make complex, stable structures possible, such as the existence of stable planetary orbits and the particular behavior of electromagnetic forces. But this anthropic reasoning, while intriguing, does not yet constitute a fundamental physical explanation. Why space has exactly 3 large dimensions, and whether the other dimensions predicted by some theories truly exist in some curled or hidden form, is one of the most quietly deep questions at the frontier of fundamental physics. It is a mystery that invites not urgency, but a long and comfortable contemplation. The mystery of the neutrino's mass. Neutrinos are among the most abundant particles in the universe, produced in enormous quantities in the hearts of stars, in the aftermath of supernova explosions, and in the Big Bang itself, and yet they are so remarkably ghostly that billions of them pass through your body every second without interacting with a single atom, like the quietest of all cosmic visitors slipping through walls as though they were not there. For decades, the standard model of particle physics assumed neutrinos had no mass whatsoever, but experiments in the late 1990s revealed that neutrinos do in fact oscillate between different types as they travel, a behavior only possible if they carry some small but non-zero mass. Yet the precise values of these masses remain unmeasured, and understanding why the neutrino masses are so extraordinarily small, far tinier than the masses of other fundamental particles, is one of the most delicate open questions in particle physics. The asymmetry between neutrino and antineutrino properties may also hold clues to the great mystery of why the universe contains more matter than antimatter. The mystery of stellar nurseries. Deep within the spiral arms of galaxies like our own Milky Way, there exist vast and beautiful clouds of cold, dark gas and dust known as molecular clouds. Enormous structures stretching across hundreds of light years, so cold and dense in their interiors that molecules of hydrogen, carbon monoxide, and water ice can form and persist in the quiet dark. Within these clouds, gravity slowly gathers knots of material that grow ever denser, warming as they contract, until eventually a protostar ignites at the center of each knot and begins its long, gradual journey toward becoming a full-fledged star. The details of how star formation proceeds, how quickly it happens, what determines the mass of the resulting star, and how much of the surrounding material is blown away by the young star's winds and radiation, are still being gently worked out through a combination of observation and simulation. The Orion Nebula, visible on clear winter nights as a soft, glowing patch in the sword of the Orion constellation, is perhaps the most beautiful and studied of these stellar nurseries, and it continues to reveal new details about the quiet, wondrous process of stellar birth. The mystery of magnetic fields in galaxies. Running through the vast, diffuse interstellar medium of spiral galaxies like threads of invisible silk are large-scale magnetic fields, not strong by any laboratory standard, but coherent and organized across distances of thousands of light years in a way that continues to quietly puzzle astrophysicists who study how they arose and what maintains them. These galactic magnetic fields influence the motion of charged particles and cosmic rays, shape the conditions under which stars form in molecular clouds, and participate in the dynamics of the interstellar medium in complex and not fully understood ways. The leading explanation for their origin involves a dynamo process, in which the differential rotation of the galaxy and turbulent motions in the interstellar medium work together to amplify seed magnetic fields. But the details of how the process operates over cosmic time and how the field achieves its organized, large-scale structure remains an area of active and quietly engaged research. The idea that entire galaxies are laced through with invisible but structured magnetic filaments adds a layer of quiet complexity to the already extraordinary tapestry of cosmic structure. The mystery of the observable universe's edge. The universe we are able to observe is bounded not by a wall or an edge in the usual sense, but by a horizon created by the finite speed of light and the finite age of the cosmos. Light from regions farther away than roughly 46 billion light-years has simply not had enough time to reach us since the Big Bang, and so beyond that distance, which forms the edge of our observable universe, everything lies in a permanent and peaceful darkness as far as our instruments are concerned. Within our observable universe, there are estimated to be somewhere in the range of 2 trillion galaxies, each containing hundreds of billions of stars, each with potentially many planets drifting in orbit around them, and all of this is just the small, illuminated portion of what may be a much larger or even infinite cosmos extending silently beyond our horizon. What lies beyond that gentle boundary, whether the same kinds of galaxies and structures continue indefinitely, or whether conditions change in ways we cannot observe or predict, is a question that is, perhaps almost by definition, unanswerable in any direct way. Yet it invites a kind of profound and peaceful awe, a resting of the imagination against the outermost limits of what can ever be known. The mystery of gravitational waves. For most of human history, our view of the universe was built entirely from light, from the photons that travel across space and eventually enter our eyes or our telescopes, bringing with them the stories of distant stars and galaxies. But in September 2015, the LIGO Observatory detected for the very first time something entirely different. A gravitational wave, a ripple in the fabric of spacetime itself produced by the merger of two black holes roughly 1.3 billion light-years away, a signal so incredibly faint that it required the most sensitive instruments ever built to detect a displacement 1,000 times smaller than the diameter of a proton. This detection opened an entirely new sense through which humanity could listen to the universe, hearing rather than seeing the most energetic events in the cosmos through the gentle stretch and squeeze of space itself. The landscape of gravitational wave astronomy is still in its infancy, and what further wonders await discovery as detectors grow more sensitive over the coming decades is a question of deep and quietly luminous anticipation. The mystery of the Higgs field. In 2012, the discovery of the Higgs boson at the Large Hadron Collider near Geneva completed the standard model of particle physics, confirming the existence of a field that permeates all of space and gives mass to the fundamental particles that drift and interact within it. The Higgs field is not like other fields. It does not diminish with distance, but instead has the same non-zero value everywhere in the universe, like a smooth, invisible medium that particles must push through to acquire their characteristic masses. What remains quietly puzzling is why the Higgs field has exactly the value it does, a value that seems precariously poised between two different behaviors and requires a degree of fine-tuning that many physicists find aesthetically uncomfortable. Understanding the deeper reason for the Higgs field's value, and whether other as-yet undiscovered fields or particles help to stabilize it, is one of the most elegant and gently open questions at the frontier of high-energy physics. The mystery of the arrow of entropy. There is a quiet and persistent asymmetry in the way the universe behaves over time, one that we encounter every day in the way that ice melts into water but water never spontaneously freezes into ice, in the way that a drop of ink spreads through a glass of water but never gathers back into a drop on its own. This tendency of physical systems to drift toward states of greater disorder, measured by the quantity physicists call entropy, gives time its felt direction, its gentle arrow pointing always from past toward future. The second law of thermodynamics tells us that in a closed system, entropy never decreases, and yet the deep question of why the early universe had such extraordinarily low entropy, from which it has been drifting upward ever since, remains one of the most beautifully open questions in all of physics. Some researchers have suggested that the low entropy of our cosmic beginning may be connected to the nature of the Big Bang itself, or to the existence of gravitational degrees of freedom that are not yet fully accounted for in our statistical descriptions of the universe. The mystery of sunspot cycles. Every approximately 11 years, the sun passes through a cycle of activity that moves from a quiet solar minimum, when the face of the sun is relatively smooth and calm, to a solar maximum, when the surface is dotted with dark sunspots, arching magnetic filaments, and frequent eruptions of plasma. A slow, rhythmic breathing that has been observed and recorded for centuries. The sunspots themselves are regions of intense magnetic field that suppress the convective motion of hot plasma from below, making them slightly cooler than their surroundings and giving them their characteristic dark appearance against the brilliant solar surface. What remains not entirely understood is the precise mechanism by which the sun's magnetic field reverses polarity during each cycle, how the cycle's length and intensity are determined, and what drives the occasional longer periods of reduced activity known as grand solar minima. The sun, our nearest and most familiar star, continues to guard certain of its rhythms behind a warm veil of not yet understood complexity. The mystery of ultra-hot Jupiters. Among the diverse population of planets discovered orbiting other stars, one of the most quietly perplexing categories is that of the ultra-hot Jupiters, enormous gas giant planets orbiting their parent stars at distances so small that they complete an orbit in only a day or two, locked in a tidal embrace that keeps one face perpetually in blazing, radiation-drenched day and the other in permanent, cold night. The atmospheric temperatures on the day side of these worlds can reach 2,500 to 4,000 degrees Celsius, hotter than many stars, while iron and silicate minerals evaporate into the atmosphere and condense into clouds on the cooler night side before raining back down as liquid droplets of metal. How these massive worlds came to occupy their current close orbits, so different from the outer positions where gas giants like Jupiter are thought to form in a young solar system, is a question that has led to rich theoretical work on planetary migration through the gas disks that surround young stars. They are worlds of quiet extremity, carrying out their year in a single Earth day, blanketed in an atmosphere of liquid metals and ionized gases. The mystery of the interstellar medium. The space between the stars is not truly empty, but filled with a thin, diffuse mixture of gas, dust, and cosmic rays known as the interstellar medium. A vast and complex environment that is simultaneously one of the most tenuous substances in the universe and one of the most important, serving as the reservoir from which new stars form and into which dying stars return their material in a slow, graceful cycle of cosmic recycling. The interstellar medium exists in multiple phases simultaneously, regions of hot, ionized gas at millions of degrees mingling with cooler atomic and molecular clouds, all held together by the large-scale gravitational structure of the galaxy. The detailed physics of how these different phases coexist, how turbulence shapes the structure of the medium, and how magnetic fields influence the flow of material through it remain areas of rich and ongoing research. There is something quietly beautiful about the thought that the space between the stars is not silence but a complex, slowly moving medium, full of invisible chemistry and quiet motion. The mystery of time dilation. One of the most gently extraordinary discoveries of 20th century physics was the realization that time does not flow at the same rate for all observers, that a clock moving at high speed relative to a stationary one will tick more slowly, and a clock placed at the bottom of a gravitational well will tick more slowly than one floating freely in space. This phenomenon, predicted by Einstein's theories of special and general relativity and confirmed through countless experiments including the precise timekeeping of GPS satellites, means that time is not the absolute, universal constant it was once imagined to be, but rather a flexible and relative quantity that bends around mass and motion. What remains philosophically and physically open is the deeper reason why time behaves this way, why the geometry of spacetime should be such that mass curves not only space but also the rate at which time flows. The answer, if it exists in a form beyond the current mathematical framework, lies somewhere in the not yet achieved unification of general relativity and quantum mechanics, resting quietly at the frontier of physics like a door not yet opened. The mystery of antimatter regions of the universe. While the observable universe appears to be composed overwhelmingly of matter rather than antimatter, some researchers have quietly entertained the possibility that there might exist regions of the universe, perhaps entire galaxies or clusters, composed primarily of antimatter, separated from matter-dominated regions by vast distances that prevent the annihilating encounters that would otherwise occur at their boundaries. If such antimatter galaxies existed, they would be indistinguishable from matter galaxies through ordinary light alone, since a photon and its antiparticle are identical, and only at the boundary between regions would the characteristic radiation of matter-antimatter annihilation betray their nature. Searches for this characteristic annihilation radiation at cosmic scales have so far found no evidence for large antimatter regions, suggesting that if they exist at all, they are separated from us by distances larger than the observable universe. The question of whether the imbalance between matter and antimatter is a universal constant or merely a local feature remains one of the quieter but most profound open questions in cosmological physics. The mystery of how planets form. The story of how a flat disk of gas and dust swirling around a young star assembles itself, over millions of years, into the orderly architecture of a planetary system, with rocky inner planets, gas giants at intermediate distances and icy bodies in the outer reaches, is one that planetary scientists have made great progress in understanding and that still harbors deep and fascinating open questions. The first steps of planet formation, in which tiny dust grains collide and stick together to form pebbles and then larger aggregates called planetesimals, are reasonably well understood, but the intermediate phase, in which planetesimals somehow overcome the barriers that should cause them to bounce off one another or break apart rather than accumulating further, remains an area of active and genuinely open research. The diversity of planetary system architectures discovered around other stars, many of them nothing like our own solar system, has added layers of beautiful complexity to the theoretical picture and suggests that planet formation is a process with many possible outcomes. Each discovery of a new and unexpected planetary system adds a soft, new data point to a puzzle whose full picture is still slowly coming into focus. The mystery of the cosmic dawn. Among the most exciting frontiers of modern astronomy is the era known as cosmic dawn, the period roughly between 200 million and 1 billion years after the Big Bang, when the first generations of stars began to ignite within the darkness of the early universe, their ultraviolet radiation gradually ionizing the surrounding neutral hydrogen in a process called reionization that transformed the cosmos from an opaque, foggy state into the transparent, light-filled universe we see today. The James Webb Space Telescope has already begun detecting light from some of the very earliest galaxies ever observed, peering back to within a few hundred million years of the Big Bang and revealing structures that have surprised astronomers with their early maturity and unexpected brightness. How those first stars and galaxies formed and grew so quickly, and exactly how and when the process of reionization unfolded across the cosmic landscape, are questions that astronomers are now in the exciting early stages of directly observing and answering. We are, in a sense, watching the universe slowly light itself up for the first time, a gentle miracle preserved in the ancient light arriving at our telescopes after a journey of nearly 13 billion years. The mystery of Tabby's star. Among the hundreds of thousands of stars monitored by the Kepler Space Telescope in its search for transiting exoplanets, one particular star, KIC 8462852, informally known as Tabby's star after the astronomer Tabitha Boyajian who led its study, displayed a pattern of dimming unlike any other star ever observed, with irregular, aperiodic dips in brightness of up to 22% that did not match the profile of any known astronomical phenomenon. Various explanations were proposed, including swarms of comets, clouds of circumstellar dust, the remnants of a shattered planet, and even the more imaginative speculation of an advanced civilization's enormous structural engineering around the star. Subsequent observations in multiple wavelengths have generally favored an explanation involving circumstellar dust, which tends to dim shorter wavelengths of light more than longer ones, a pattern consistent with what was measured. And yet the precise nature of this unusual star's surroundings, and the history of whatever event or process is responsible for its extraordinary behavior, remains gently and beautifully unresolved in all its specific detail. The mystery of magnetic monopoles. In our everyday experience of magnetic objects, from a simple refrigerator magnet to the most powerful superconducting magnets in physics laboratories, magnetic poles always come in pairs, a north and a south inseparably bound together, so that cutting a magnet in half never produces an isolated north pole or an isolated south pole, only two smaller magnets each with its own paired poles. And yet, in 1931, the great theoretical physicist Paul Dirac showed that the existence of even a single isolated magnetic monopole, a magnetically charged particle analogous to an electrically charged particle, anywhere in the universe would elegantly explain why electric charge comes in discrete, quantized units. Many theories of physics beyond the Standard Model, including grand unified theories, actually predict that monopoles should have been produced in enormous quantities in the early universe. Despite careful and wide-ranging searches, no magnetic monopole has ever been definitively detected, and where they all went, if they ever existed, is one of the quiet puzzles that sit at the intersection of particle physics and cosmology. The mystery of helioseismology and the solar interior. Much as geologists use seismic waves to probe the interior of the Earth, waves generated by earthquakes that travel through the planet's layers and emerge changed by what they have passed through. Solar scientists can use acoustic oscillations on the surface of the Sun to peer into its deep interior in a technique known as helioseismology. By carefully analyzing the frequencies and patterns of the Sun's gentle surface vibrations, scientists have assembled a detailed picture of the internal structure of the Sun, including the rotation rates of its different layers and the location of the boundary between the convective outer zone and the radiative interior below. And yet certain aspects of the solar interior remain puzzling, including the precise abundances of elements like oxygen and neon deep within the Sun, which have been the subject of a long-running and still unresolved discrepancy between spectroscopic measurements and helioseismological inferences. The Sun patiently holds some of its innermost secrets behind the brilliant curtain of its surface, yielding them only slowly and in pieces to our most careful and indirect methods of inquiry. The mystery of Hawking radiation. In 1974, the physicist Stephen Hawking made a remarkable theoretical prediction that changed how scientists think about black holes. He showed that when the strange quantum mechanical behavior of space in the vicinity of a black hole's event horizon is properly accounted for, a black hole should actually slowly emit a faint trickle of thermal radiation, now known as Hawking radiation, gradually losing mass over an almost incomprehensibly long time until it eventually evaporates entirely. For a black hole the mass of the Sun, this evaporation would take approximately 10 to the power of 67 years, a number so far beyond any human conception of time that it exists only as a mathematical abstraction. 4 tiny, hypothetical primordial black holes formed in the early universe, the evaporation would happen on a shorter timescale, and their final moments would produce a brief burst of energy. Hawking radiation has never been directly observed, it is far too faint for any instrument yet devised to detect, and it remains one of the most beautifully theoretical and important predictions in all of physics, sitting quietly at the crossroads of quantum mechanics and general relativity. The mystery of how the first elements were made. In the first few minutes after the Big Bang, the universe was a hot, dense, rapidly cooling sea of protons and neutrons undergoing furious nuclear reactions in a process known as Big Bang nucleosynthesis. And in those few brief, extraordinary minutes, essentially all of the hydrogen and helium in the universe was formed, along with tiny traces of lithium and beryllium, before the universe cooled below the temperature at which nuclear fusion could continue. The precise proportions of these primordial elements, approximately 75% hydrogen and 25% helium by mass, with just traces of everything else, were determined by the conditions in those first minutes and are a powerful constraint on cosmological models. Everything heavier than lithium, from the carbon in your body to the silicon in the rocks beneath the ground and the iron in the Earth's core, was formed billions of years later in the nuclear furnaces of stars and in the cataclysmic deaths of massive stars and supernova explosions. The quiet fact that we are literally made of stardust, assembled over billions of years from material forged in the hearts of long-dead stars, is among the most gently humbling and beautiful ideas that science has ever placed before us. The mystery of white holes. In the mathematics of general relativity, the equations that describe a black hole, a region of space from which nothing, not even light, can escape once it crosses the event horizon, have a theoretical time-reversed counterpart known as a white hole, a region of space that cannot be entered from outside but from which matter and light continuously emerge, like a black hole running backward through time. White holes have never been observed, and there is currently no known physical process that would produce one, yet they arise naturally within the mathematical structure of the theory and have intrigued physicists and theorists for decades. Some speculative theories have proposed connections between black holes and white holes through tunnels in spacetime called Einstein-Rosen bridges, or wormholes, offering the romantic notion of passages between distant regions of the universe or even between different universes entirely. Whether white holes exist anywhere in the cosmos, or whether they are beautiful but purely mathematical objects with no physical reality, is one of the quietly compelling open questions that general relativity gently leaves on the table. The mystery of the zodiacal light. On very dark, clear nights far from artificial light pollution, careful observers can sometimes see a soft, faint cone of light rising from the horizon where the sun has recently set, tilting upward along the ecliptic, the plane of the solar system, in a gentle, ethereal glow known as the zodiacal light. This diffuse illumination is caused by sunlight scattering off countless tiny dust particles distributed throughout the inner solar system, particles estimated to be roughly 10 to 300 micrometers in diameter and suspended in a flat, lens-shaped cloud stretching from the vicinity of Mercury outward past the orbit of Mars. The precise sources of this dust, whether it comes primarily from cometary debris shed as comets pass near the Sun, from collisions among asteroid belt objects, or from material streaming in from the outer solar system, has been a matter of quiet ongoing research. NASA's Parker Solar Probe and other recent missions have provided new data suggesting that at least some of the dust originates from the very near vicinity of the Sun, adding new texture to our understanding of this ancient, peaceful glow. The mystery of stellar population 3 stars. The very first stars to ignite in the universe were made of an extraordinarily pure mixture of hydrogen and helium. None of the heavier elements forged in subsequent generations of stellar evolution yet existed, and these primordial luminaries, known to astronomers as population 3 stars, are thought to have been among the most massive objects ever to exist, possibly hundreds of times more massive than our Sun, burning with a brilliant blue-white intensity before consuming their fuel and ending their brief, spectacular lives in enormous supernova explosions that seeded the surrounding space with the first heavy elements. None of these first-generation stars survives today. They were too massive and burned too quickly, living lives measured in millions rather than billions of years, and so they have never been directly observed. Their existence is inferred from theory and from the chemical compositions of the oldest second-generation stars that do survive, which carry within them the fingerprint of the material scattered by their predecessors. The James Webb Space Telescope has begun searching the most distant reaches of the observable universe for evidence of these ancient, brilliant, peacefully vanished first stars. The mystery of the cosmic web. When cosmologists model the large-scale distribution of matter in the universe using computer simulations, they consistently produce a structure of breathtaking complexity, a cosmic web of long, thin filaments of dark matter and gas stretching across hundreds of millions of light years, connecting at their intersections in dense knots where galaxy clusters reside, and enclosing vast, empty voids within their gossamer meshwork. This structure, predicted by the cold dark matter model of the universe, has been observed through the positions of millions of galaxies mapped by large sky surveys, confirming with quiet elegance that the universe is organized at the very largest scales into this intricate, beautiful web. The filaments themselves, though too diffuse to be directly imaged in their entirety, contain within them much of the ordinary matter in the universe in the form of a warm, rarefied intergalactic gas that has only recently begun to be detected through its faint emission and absorption of ultraviolet light. Understanding the detailed physics of how matter flows along and within the filaments, and how the web continues to slowly evolve under the combined influence of gravity and dark energy, is one of the gentle ongoing projects of modern observational and theoretical cosmology. The mystery of dark energy's equation of state. The mysterious dark energy that is believed to be driving the accelerating expansion of the universe is described mathematically by a quantity known as its equation of state, a number that characterizes how the pressure of dark energy relates to its energy density, and whose value determines how the universe's expansion will change over time. Current observations are consistent with dark energy being a cosmological constant, a perfectly uniform energy density filling all of space with a constant value that does not change as the universe expands, which would correspond to an equation of state parameter of -1, a value named after Einstein, who first introduced the concept. But within the observational uncertainties, dark energy could also be something more dynamic, a field that changes over time in ways that would cause the expansion to accelerate at a different rate in the future than it does today. Distinguishing between these possibilities requires measurements of extraordinary precision, and next-generation telescopes and surveys are being designed with exactly this question among their primary scientific goals. The mystery of solar system formation timing. The Sun and its family of planets are believed to have formed approximately 4.6 billion years ago from the gravitational collapse of a cloud of gas and dust in one of the Milky Way's spiral arms, a cloud that may have been gently nudged into collapse by the shockwave of a nearby supernova, triggering the formation of our solar system in a moment of stellar influence from a long-vanished neighbor. The radioactive isotopes preserved within the most ancient meteorites that fall to Earth carry within them a record of this early history, like tiny frozen clocks that have been ticking since the earliest solid material in the solar system first condensed from the swirling disk of gas and dust around the young sun. Some of these isotopes, such as aluminum-26, which decays in about 700,000 years, were present in abundance in early solar system material, indicating that they must have been freshly forged in a nearby stellar explosion and incorporated into the cloud before they could decay. The detailed reconstruction of the sequence of events that led to our solar system's formation from these ancient, patient isotopic records continues to be a source of quiet wonder and careful scientific inquiry. The mystery of the observable versus actual universe. The observable universe, the spherical region of space from which light has had enough time to reach us since the Big Bang, extends approximately 46 billion light-years in every direction, a volume containing an estimated 2 trillion galaxies and all the matter and energy that we can ever hope to observe with any instrument. But this observable universe is almost certainly just a small, illuminated bubble within a vastly larger total universe, which may extend far beyond our cosmic horizon in every direction for a distance that could, in some models, be infinite. If the universe beyond our horizon is similar in composition and structure to what we can observe, then the number of galaxies, stars, and planets beyond our reach would dwarf the already incomprehensible number we can see. And if space is truly infinite, then every possible arrangement of matter would repeat itself somewhere out there in the quiet, dark beyond. Whether the universe is truly infinite or merely very large, and what lies beyond the gentle boundary of our observational horizon, is a question that resides peacefully in the realm of philosophy as much as physics. The mystery of metallic hydrogen. Deep within the immense interiors of the giant planets Jupiter and Saturn, where pressures reach millions of times the atmospheric pressure at Earth's surface, hydrogen, the simplest and most abundant element in the universe, is believed to undergo a remarkable transformation, shifting from its familiar gaseous form through a liquid state and then into a metallic phase in which electrons are no longer bound to individual atoms but flow freely through the compressed material like the electrons in a conducting metal. This exotic state of matter, known as metallic hydrogen, was predicted by theoretical physicists decades ago, and scientists believe it is responsible for the powerful magnetic fields of Jupiter and Saturn through a dynamo effect driven by its flowing currents. Creating and sustaining metallic hydrogen in a laboratory has proven extraordinarily difficult, though brief and tentative claims of its creation have been made in experiments using diamond anvil cells, and the conditions under which it becomes stable remain an area of active research. The deepest interior layers of our solar system's largest planets are thus composed of a material that we have never held in our hands, pressing quietly under pressures beyond anything achievable on the surface of the Earth. The mystery of the hydrogen 21 centimeters line. Neutral hydrogen atoms scattered throughout the interstellar and intergalactic medium have a tendency to occasionally emit a photon at a very specific wavelength of 21 centimeters. Produced when the electron in the hydrogen atom gently flips its spin state relative to the proton at the atom's center. And this radio emission serves as one of the most important tools in radio astronomy for mapping the distribution of hydrogen across the Milky Way and other galaxies. Because hydrogen is by far the most abundant element in the universe, and because this 21-centimeter emission passes through the dust clouds that obscure optical telescopes, it provides a unique, deep, and penetrating view of the galaxy's structure and of the motions of gas in the arms and disk of the Milky Way. Scientists are now building instruments of enormous scale, including the Square Kilometre Array in South Africa and Australia, to use this same hydrogen signal to probe the three-dimensional distribution of gas across billions of light-years and deep into the era of cosmic reionization. The quiet flip of an electron's spin, occurring in atoms scattered across the cosmos, thus becomes one of the most informative whispers the universe has to offer. The mystery of stellar ages. When astronomers look at a collection of stars in a cluster, or compare the ages of stars across different regions of the galaxy, they use a variety of methods to determine how old those stars are, including the precise chemical compositions in their spectra, the position of their turn-off point on the Hertzsprung-Russell diagram of stellar luminosity versus temperature, and the measured abundances of long-lived radioactive isotopes. The ages of the oldest stars in the Milky Way, known as metal-poor globular cluster stars, have been measured at approximately 13 to 13.8 billion years, very close to the age of the universe itself, which provides a beautiful independent confirmation of the universe's age derived from cosmological observations. And yet certain aspects of stellar age dating carry systematic uncertainties that are still being carefully refined, including the precise values of atomic parameters used in stellar atmosphere models and the detailed treatment of convection and mixing in stellar interiors. Every improvement in our ability to date stars with precision tells a clearer and more detailed version of the universe's autobiography, one quietly patient measurement at a time. The mystery of the solar neutrino problem's resolution. For several decades of the 20th century, physics and astrophysics were quietly troubled by a discrepancy known as the solar neutrino problem. The observation that the number of neutrinos detected arriving at Earth from the Sun's nuclear core was only about 1/3 to 1/2 of what theoretical models of the Sun's interior confidently predicted should be produced. This discrepancy was finally resolved in the early 2000s by the discovery that neutrinos possess the ability to oscillate, to change between three different types or flavors as they travel through space, meaning that a large fraction of the electron neutrinos produced in the Sun's core were transforming into muon or tau neutrinos during their journey to Earth, becoming invisible to detectors that were only sensitive to the electron type. This resolution required neutrinos to have a non-zero mass, an unexpected revision to the standard model of particle physics, and won the scientist who demonstrated it a Nobel Prize. The solar neutrino problem thus sits as one of the most beautifully instructive examples in the history of science of a persistent discrepancy patiently pointing the way to genuinely new physics. The mystery of Earth's magnetic field. The magnetic field that surrounds the Earth, deflecting the solar wind, guiding migratory birds, and making compass needles align themselves in soft, quiet obedience to the planet's north pole, is generated deep within the Earth's interior by the circulation of liquid iron in the outer core, a churning, convecting sea of molten metal some 2,200 kilometers thick rotating around the solid inner core. The precise dynamics of this geodynamo are complex and not fully understood, but scientists do know that the geomagnetic field is not stable on geological timescales. It has reversed its polarity hundreds of times over the course of Earth's history, with north becoming south and south becoming north in a process that typically unfolds over thousands of years. The timing and mechanisms of these reversals, and what conditions in the outer core's convective dynamics trigger them, remain an area of active research in geophysics. What the Earth's interior looks like in full detail, its structure, composition, and the intricate flows of metal that generate our protective magnetic shield, continues to be mapped and refined through the patient, gentle analysis of seismic waves. The mystery of the speed of light as a constant. Among the most deeply mysterious and foundational results in all of physics is the experimentally confirmed fact that the speed of light in a vacuum, approximately 299,792 kilometers per second, is the same for all observers regardless of their state of motion or the motion of the source that emitted the light, a result so strange and counterintuitive that it occupied Albert Einstein's imagination for years before he constructed the special theory of relativity around it. This constancy of the speed of light has been confirmed to extraordinary precision by countless experiments and forms the bedrock upon which both special and general relativity are built, leading to all the remarkable consequences of those theories including time dilation, length contraction, and the equivalence of mass and energy. What remains philosophically and perhaps physically open is the deeper reason why the speed of light has this specific value, and whether it is truly a universal constant or might change over enormous cosmic timescales or in extreme physical conditions. The speed of light is, in a sense, the ultimate speed limit of the universe, a quiet, absolute boundary woven into the very structure of spacetime. The mystery of the Tunguska event's detailed composition. On the morning of June 30, 1908, something extraordinary and peaceful in its aftermath entered the atmosphere over the remote Siberian taiga near the Podkamenya Tunguska River, exploding at an altitude of roughly 5 to 10 kilometers with a force estimated at 10 to 15 megatons of TNT, an airburst so powerful that it flattened an estimated 2,000 square kilometers of forest, knocking trees outward in a radial pattern centered on the explosion point, and sending shockwaves that were detected by barometric stations across Eurasia. Because the explosion occurred in one of the most remote and sparsely populated regions on Earth, and because the first scientific expeditions to the site did not arrive until nearly 20 years later, the physical evidence was limited. The consensus of modern research holds that the culprit was a small stony asteroid or comet fragment that disintegrated in the atmosphere before reaching the ground, but the precise composition, size, and trajectory of the object, and the exact sequence of events during its atmospheric entry, have been reconstructed only indirectly. Tiny silicate and magnetite spherules found in peat layers at the site, along with geochemical anomalies, continue to be gently studied as quiet residues of that ancient, distant morning. The mystery of dark matter candidates. Although the evidence for dark matter's gravitational effects is extraordinarily robust and consistent across many different types of astronomical observation, the identity of the particles or objects that constitute dark matter remains one of the most profound open questions in all of science. For decades, the leading candidate was a class of hypothetical particles known as weakly interacting massive particles, or WIMPs, which would interact with ordinary matter only through gravity and the weak nuclear force and would have masses in a range accessible to detection by sensitive underground detectors. Despite increasingly sensitive searches using detectors buried deep in salt mines and mountain tunnels to shield them from other sources of radiation, no WIMP has ever been definitively detected. Other candidates include axions, light, weakly interacting particles predicted by extensions of the Standard Model, sterile neutrinos, and hypothetical primordial black holes formed in the early universe. The dark matter puzzle remains beautifully open, with its solution promising to reshape our understanding of fundamental physics in quiet but profound ways. The mystery of the Milky Way's central bar. Our own Milky Way galaxy, viewed from the outside, would appear not as a simple pinwheel of spiral arms but as a barred spiral galaxy, a structure with a long, roughly linear bar of stars running through its central region, from the ends of which the spiral arms extend outward in graceful, curving sweeps of blue-white stars and dark dust lanes. This central bar, extending roughly 27,000 light-years in length, is composed of billions of old reddish stars that have been channeled by gravitational resonances into this elongated, rotating structure, and its rotation is thought to be slightly misaligned with the overall rotation of the galaxy's disk. How the bar formed, how it is maintained against the forces that would otherwise tend to dissolve it back into a circular distribution, and how it influences the flow of gas and the rate of star formation in the inner galaxy are questions that are still being investigated through a combination of observations and numerical simulations. We look outward at other barred spiral galaxies to understand what we ourselves would look like from afar, mapping our own home through the quiet intelligence of analogy. The mystery of Pluto's heart. When NASA's New Horizons spacecraft completed its flyby of the distant dwarf planet Pluto in July 2015, one of the most immediately striking features it revealed was a vast, heart-shaped region of pale nitrogen ice plains on Pluto's surface, subsequently named Tombaugh Regio in honor of the astronomer who discovered Pluto in 1930. The bright, left lobe of the heart, known as Sputnik Planitia, is a roughly 1,000-kilometer wide impact basin filled with flowing nitrogen ice that is slowly turning over in a process of convective overturn, renewing its surface and giving it a remarkably smooth and youthful appearance. What geologists are still quietly debating is how the basin formed, how Pluto's internal heat is sufficient to drive the convection of the nitrogen ice in its frigid environment, and why Sputnik Planitia is positioned almost directly opposite from Pluto's largest moon Charon, a position some researchers think may be related to a tidally induced reorientation of the entire dwarf planet. Pluto, at the edge of the solar system and barely glimpsed, turns out to be a place of surprising geological activity and quiet, frozen beauty. The mystery of quark-gluon plasma. In the first moments after the Big Bang, the universe was so extraordinarily hot and dense that quarks and gluons, the fundamental constituents of protons and neutrons, could not combine into the composite particles we know today, but instead existed freely in a state known as quark-gluon plasma, a dense, swirling soup of fundamental particles interacting freely over distances that would normally confine them within individual protons and neutrons. This exotic state of matter has been recreated briefly and on a tiny scale in high-energy particle collisions at facilities like the Large Hadron Collider at CERN and at the Relativistic Heavy Ion Collider in New York, where gold or lead nuclei are smashed together at nearly the speed of light to produce a fleeting droplet of quark-gluon plasma lasting only fractions of a second. The surprising discovery from these experiments is that quark-gluon plasma behaves not like a gas as originally expected, but more like a nearly perfect liquid with extraordinarily low viscosity, a property that remains one of the more quietly intriguing and theoretically challenging results in contemporary nuclear physics. We are in these brief experimental moments, recreating a tiny piece of the universe as it existed in its very first microsecond. The mystery of how the moon stabilizes Earth. Among the many quiet ways in which the moon's presence shapes the conditions on Earth, one of the most profound is its gravitational stabilization of the Earth's axial tilt, the 23.5-degree angle at which the Earth's rotational axis is tilted relative to its orbital plane, an angle that produces the gentle, familiar progression of the seasons. Computer simulations suggest that without the moon's stabilizing gravitational influence, the Earth's axial tilt could vary chaotically over millions of years, swinging between near zero and more than 85 degrees in erratic, unpredictable ways that would subject the planet to extreme climatic oscillations far greater than anything experienced in Earth's actual geological record. The moon's mass and distance combine to create a gravitational torque that damps this instability, keeping the axial tilt within a relatively narrow range over geological timescales. Whether this stabilization was necessary for the development of complex life on Earth, or whether life could have adapted to the more chaotic climate that would have resulted from a moonless world, is one of the gentle questions at the intersection of planetary science and astrobiology. The mystery of atmospheric oxygen's rise. For roughly the first 2 billion years of Earth's history, the planet's atmosphere contained virtually no free oxygen. The gas was produced by early photosynthetic microorganisms but was consumed almost as fast as it was made by reactions with dissolved iron in the ancient ocean and by volcanic gases. Then, approximately 2.4 billion years ago, the oxygen content of the atmosphere rose sharply in what geologists call the Great Oxidation Event, a transformation that permanently altered the chemistry of the atmosphere, the oceans, and the surface rocks, and that created the conditions for the eventual evolution of complex, oxygen-breathing life. What triggered this sudden rise after so many hundreds of millions of years remains a subject of active and quietly engaged scientific debate, with proposed explanations including changes in the rate of hydrogen escape from the atmosphere, the saturation of geological sinks for oxygen, and changes in the style of tectonic activity. The Great Oxidation Event reshaped our entire planet and laid the quiet, chemical foundation for everything that followed in the history of life on Earth. The mystery of red sprites and blue jets. High above ordinary thunderstorms, in the dark and quiet reaches of the upper atmosphere between roughly 40 and 90 kilometers altitude, there occur some of the most visually extraordinary and scientifically puzzling electrical phenomena on Earth. Transient luminous events with evocative names such as red sprites, blue jets, and elves, which flash for only milliseconds in the thin air above storm systems before disappearing as suddenly as they appeared. Red sprites are large, diffuse reddish glows that can extend vertically for tens of kilometers above the tops of storm clouds, triggered by the electric fields associated with positive lightning strokes below, while blue jets are narrower, upward-reaching cones of blue light that propagate from cloud tops toward the stratosphere at extraordinary speeds. These phenomena were only systematically documented from the 1990s onward, following reports from aircraft pilots and the development of sensitive, fast cameras capable of recording their brief presence. The detailed plasma physics of how these events form, what role they play in the global atmospheric electrical circuit, and how they might influence the chemistry of the upper atmosphere remains a peaceful and ongoing area of research. The mystery of the moon's interior. The seismometers placed on the lunar surface by the Apollo missions between 1969 and 1977 detected thousands of moonquakes over the years they operated, providing the first direct measurements of the moon's internal structure and opening a window into the quiet interior of our nearest neighbor in space. These measurements revealed that the Moon has a small iron core roughly 240 to 330 kilometers in radius, surrounded by a partially molten inner mantle and a solid outer mantle of rock, overlain by a thick crust that varies in thickness between the near side, which faces Earth, and the far side, which perpetually faces away. Yet many details of the lunar interior remain uncertain, including the exact size and composition of the core, the precise extent and properties of the partially molten zone, and the reasons for the dramatic asymmetry between the thinner crust on the near side and the thicker crust on the far side, a difference that may preserve clues about the Moon's early evolution. Future lunar seismic networks, planned as part of the renewed international interest in lunar exploration, promise to refine this picture and deepen our understanding of how the Moon formed and evolved over 4.5 billion years of quiet, gradually cooling existence. The mystery of cosmic string theory. String theory is one of the most ambitious and mathematically elaborate attempts in the history of physics to describe the universe at its most fundamental level, proposing that the elementary particles we know are not point-like objects but rather tiny, vibrating filaments or loops of energy whose different vibrational modes correspond to the different particles and forces we observe. One of string theory's most intriguing predictions is the possible existence of cosmic strings, not the microscopic strings of the theory, but macroscopic topological defects in the fabric of spacetime that might have formed during phase transitions in the early universe, stretching potentially across the entire visible cosmos as thin, incredibly dense, and tightly curved threads of energy. If cosmic strings exist, they would produce distinctive lensing effects on the light of background galaxies and a characteristic pattern in the cosmic microwave background, but despite careful searches, no confirmed evidence of their existence has yet been found. Whether they exist, and whether their discovery would illuminate the physics of the early universe in the deep and beautiful way that theorists have long hoped, remains a quietly open question. The mystery of the far side of the Moon. The far side of the Moon, that hemisphere that perpetually faces away from the Earth due to the tidal locking that causes the Moon to rotate at exactly the same rate as it orbits, remained entirely unseen by human eyes until 1959, when the Soviet spacecraft Luna 3 photographed it for the first time and revealed a landscape strikingly different from the near side that we see overhead on quiet nights. While the near side is dotted with large, dark volcanic plains called maria, formed by ancient lava flows filling impact basins, the far side is almost entirely covered by heavily cratered, pale highlands, with only a few small dark patches. The reasons for this dramatic asymmetry are not entirely understood, though several theories have been proposed, including the possibility that the near side's thinner crust made it more susceptible to volcanic resurfacing, and that the gravitational influence of Earth may have contributed to differences in early bombardment or heat distribution. China's Chang'e 4 mission, which achieved the first-ever soft landing on the far side of the Moon in 2019, has begun a new era of direct exploration of this long-hidden and peacefully mysterious landscape. The mystery of bioluminescence in the deep ocean. In the profound darkness of the deep ocean, below the depth to which even the faintest traces of sunlight can penetrate, a remarkable and quietly enchanting phenomenon prevails. The majority of living organisms produce their own light through bioluminescence, chemical reactions within their bodies that generate soft, cold glows of blue and green and occasionally red, used for communication, predation, camouflage, and attracting mates in the perpetual, warm darkness of the abyss. This light production is so prevalent in the deep ocean that some scientists consider bioluminescence to be the most common form of communication on Earth by sheer number of organisms involved. And yet the deep sea remains so poorly explored that we have detailed knowledge of only a small fraction of the species that live there. The specific chemical mechanisms of bioluminescence, which have evolved independently many dozens of times across the tree of life in organisms as different as bacteria, fish, jellyfish, and squid, represent a remarkable example of convergent evolution and continue to be studied both for their biological significance and for the biotechnological applications that understanding them makes possible. The deep ocean, a vast, dark, quietly living world beneath our feet, remains one of the least explored environments on Earth. The mystery of the Pioneer spacecraft's longevity. When engineers at NASA designed and built the Pioneer 10 and Pioneer 11 spacecraft in the early 1970s, they were creating vehicles intended to make the first close flyby of Jupiter and, in Pioneer 11's case, Saturn, before heading outward on their long, slow journeys into interstellar space. Missions that were considered successful if the spacecraft survived long enough to transmit data from the vicinity of those distant planets. And yet Pioneer 10 continued to return faint signals from a distance of over 12 billion kilometers until 2003, more than 30 years after its launch, when its nuclear power source had finally decayed beyond the ability to power its transmitter, making it among the longest operating spacecraft in history. The longevity of these craft, and the data they quietly gathered over decades of drifting through the outer solar system, provided decades of opportunity to study the environment of the heliosphere and the subtle forces acting on objects in deep space. Today, Pioneer 10 is the fourth farthest human-made object from the Sun, drifting in the direction of the constellation Taurus at approximately 2.6 astronomical units per year, carrying with it a golden plaque designed to communicate humanity's nature and location to any civilization that might ever encounter it. The mystery of the spin-orbit resonances in the solar system. Throughout the solar system, the gravitational interactions between orbiting bodies and the objects they orbit create gentle, long-lasting gravitational relationships known as orbital resonances. Relationships in which the orbital periods of two bodies form simple integer ratios that cause them to exert regular, reinforcing gravitational nudges on one another. Mercury, for instance, rotates exactly 3 times for every 2 of its orbits around the Sun, a 3:2 spin-orbit resonance maintained by the gentle but persistent tidal forces of the Sun's gravity. In the asteroid belt, the Kirkwood gaps are regions where almost no asteroids exist because the orbital period at those distances forms a resonance with Jupiter's period, causing repeated gravitational perturbations that over long timescales slowly eject asteroids from those zones. The Pluto-Charon system, in which both bodies are tidally locked to one another and perpetually face each other across a shared axis, represents perhaps the most complete orbital resonance in the solar system, a quiet gravitational harmony maintained across billions of years. These resonances represent the solar system's way of organizing itself into stable, long-lasting patterns, a slow, gravitational music playing out across billions of years. The mystery of the Hubble tension. Among the most quietly pressing current puzzles in observational cosmology is what scientists have come to call the Hubble tension, a persistent and statistically significant disagreement between 2 different methods of measuring the current expansion rate of the universe, a number known as the Hubble constant. When cosmologists calculate the Hubble constant from observations of the early universe, specifically from the detailed pattern of the cosmic microwave background radiation, they obtain a value of approximately 67 kilometers per second per megaparsec. But when astronomers measure it directly from observations of the local universe, using the brightness of Cepheid variable stars and type Ia supernovae as distance indicators, they consistently obtain a larger value of approximately 73 kilometers per second per megaparsec. These 2 results differ by enough that random measurement errors alone are very unlikely to explain the discrepancy, suggesting either an unknown systematic error in one or both methods, or the exciting possibility that the standard cosmological model is missing some new physics. The Hubble tension has become one of the most carefully and persistently discussed topics at the frontier of modern cosmology, and its eventual resolution promises to be genuinely illuminating. The mystery of Saturn's hexagonal storm. Floating serenely at Saturn's North Pole, persistent through decades of observation by the Cassini spacecraft and Earth-based telescopes, there exists one of the most geometrically extraordinary atmospheric features in the known solar system. A vast, hexagonal cloud pattern approximately 32,000 kilometers across, each side longer than the diameter of the entire Earth, rotating with a period of roughly 10 hours and 40 minutes that precisely matches the rotation of Saturn's interior. This hexagonal jet stream, with its remarkably straight sides and sharp corners persisting in a fluid atmosphere, is thought to arise from fluid dynamic instabilities associated with the difference in wind speeds between the hexagonal jet and the surrounding atmosphere, a phenomenon that can be reproduced in rotating fluid laboratory experiments. Yet the longevity and extraordinary geometric regularity of Saturn's hexagon, which appears to have persisted unchanged for at least 4 decades of observation, represents a stability that laboratory analogs do not fully explain. At the center of the hexagon, Cassini observed a large, slowly spinning polar vortex surrounded by rings of smaller cyclonic storms, a complex arrangement of atmospheric structure resting in quiet, beautiful order at the top of the ringed planet. The mystery of ancient Mars. The surface of Mars today is cold, dry, and swept by thin, reddish winds of carbon dioxide beneath a pale sky, and yet the geological record preserved in its ancient rocks and the branching valley networks carved across its southern highlands tell a story of a dramatically different past. A Mars that, roughly 3.5 to 4 billion years ago, may have had a thicker, warmer atmosphere, liquid water flowing across its surface in rivers and possibly pooling in lakes or a shallow northern ocean. How Mars lost its thick atmosphere and its liquid water, transitioning from a relatively habitable young world to the cold, desiccated desert it is today, is a question that planetary scientists are working to answer through a combination of orbital observations, surface rover missions, and the analysis of Martian meteorites that have traveled through space and landed on Earth. The discovery of ancient river deltas and lake beds by the Perseverance rover in Jezero crater has added rich detail to this picture, and samples collected from these ancient sedimentary layers may carry within them the most direct evidence yet for whether life ever arose on early Mars. The story of Mars is the story of a world that began with remarkable promise and was gradually, quietly transformed into a place of frozen stillness and thin, rust-colored air. The mystery of the Van Allen radiation belts. Surrounding the Earth at distances of roughly 1,000 to 60,000 kilometers above the surface, held in place by the planet's magnetic field, lie two donut-shaped regions of intense radiation known as the Van Allen belts, concentrations of high-energy electrons and protons that spiral back and forth along magnetic field lines between the two poles in a perpetual, graceful dance. These belts, discovered in 1958 by instruments aboard the first American satellite Explorer 1 and named after physicist James Van Allen, pose engineering challenges for spacecraft and astronauts that must transit them, and their dynamic behavior, expanding and contracting in response to solar wind conditions, is one of the subjects of the field of space weather research. The precise mechanisms by which electrons in the outer Van Allen belt are accelerated to energies of millions of electron volts on timescales of minutes to hours during geomagnetic storms are not yet fully understood, despite decades of observation and theoretical work. These invisible, radiation-filled shells surrounding the Earth, silent and beautiful in their complexity, are a reminder that the space environment of our own planet is far richer and more dynamic than the calm blue sky visible from the ground would suggest. The mystery of stellar magnetic cycles. The Sun's 11-year cycle of magnetic activity, the slow swelling and receding of sunspot numbers, the reversals of the solar polar fields, the oscillation of flares and coronal mass ejections, is the best-studied magnetic cycle of any star, and yet the precise physical mechanisms of the solar dynamo that drives it are still not fully understood in their details. When astronomers observe other Sun-like stars using the same techniques that detect the Sun's activity cycle, they find a remarkable diversity of behavior. Some stars showing regular cycles similar to the Sun's, others showing irregular or double-peaked cycles, and others appearing to be in extended states of low activity reminiscent of the Maunder minimum, a period between about 1645 and 1715 when the Sun's surface was largely free of sunspots. Understanding what physical parameters, rotation rate, convective structure, magnetic field geometry, determine the character and regularity of a star's magnetic cycle would deepen our understanding both of stellar physics and of the long-term habitability of the planets orbiting other stars. The Sun's gentle 11-year breathing thus becomes a window into the broad diversity of stellar behavior across the galaxy. The mystery of the first galaxies. Among the most profound open questions in modern astrophysics is the story of how the very first galaxies assembled themselves in the young universe, how the initially smooth distribution of dark matter and gas in the aftermath of the Big Bang developed the seeds of structure that gradually deepened under gravity, drew in surrounding material, ignited stars, and built up over hundreds of millions of years into the luminous, structured galaxies that fill the universe today. The James Webb Space Telescope, peering further back in time than any previous instrument, has already discovered galaxies from when the universe was only a few hundred million years old, and some of these early galaxies appear to be more massive and more structured than theoretical models had predicted they could be at such early times, posing a gentle challenge to standard cosmological theory. Whether these early massive galaxies reflect new physics, the effects of dark matter behaving differently than assumed, or simply the natural variability of galaxy formation in a universe we do not yet fully understand is a question being actively investigated. We are watching, across billions of light years and billions of years, the first blooming of the cosmic garden. The mystery of Europa's potential habitability. Beneath the smooth, cracked surface of Jupiter's moon Europa, carved by the gentle flexing of tidal forces from Jupiter's immense gravity, there is believed to lie a vast, dark, liquid water ocean perhaps 100 kilometers deep, larger by volume than all of Earth's oceans combined, kept liquid not by proximity to the Sun, which is barely a distant point of pale light from Europa's orbit, but by the continuous kneading of tidal forces generating heat within the moon's rocky interior. The water in this hidden ocean is thought to be in contact with a rocky seafloor, where hydrothermal vents may release chemical energy and minerals into the water, conditions somewhat analogous to the deep-sea hydrothermal vent environments on Earth where life thrives in complete independence from sunlight. Whether the chemical ingredients and energy sources necessary for life have given rise to any form of biology in Europa's dark, silent ocean is one of the most enchanting and quietly urgent questions in the search for life beyond Earth. NASA's Europa Clipper spacecraft, launched in October 2024, is now on its way to Jupiter to study Europa's ocean in unprecedented detail over dozens of close flybys beginning in 2030. The mystery of gravitational lensing's deepest reaches. One of the most beautiful and useful phenomena in all of observational astronomy is gravitational lensing, the bending and magnification of light from distant background objects by the gravity of massive foreground objects such as galaxy clusters, as predicted by Einstein's general theory of relativity and first confirmed observationally during the solar eclipse of 1919. When a massive galaxy cluster lies between us and more distant galaxies, it acts as a natural cosmic telescope, bending and amplifying the light of those background galaxies into arcs, rings, and multiple images, and allowing astronomers to study galaxies that would otherwise be too faint and distant to detect. The most powerful gravitational lenses in the universe can magnify background light by factors of 10 or even 100, and by studying the patterns of lensed images, scientists can map the distribution of dark matter in the lensing cluster with exquisite precision. Some of the most distant galaxies ever detected, objects from the universe's earliest chapters, have only been found because a lucky alignment of a foreground cluster acted as a gravitational amplifier, gently gathering their ancient light and bending it toward our waiting instruments. The mystery of inflation's end. If cosmic inflation occurred in the very first fractions of a second after the Big Bang, as the majority of cosmologists believe, then at some point this extraordinary period of exponential expansion must have come to an end, with the energy that drove it being converted into the hot, dense sea of particles that filled the early universe and eventually gave rise to everything we see today, a process theorists call reheating. The details of how inflation ended and how the energy was transferred into the matter and radiation of the standard hot Big Bang are still subject to considerable theoretical uncertainty, as the fundamental nature of the inflaton field responsible for driving inflation is not known, and the particles it decayed into and the timescale over which reheating proceeded are deeply model-dependent questions. Different models of inflation ending in different ways leave subtly different observational signatures in the statistical properties of the cosmic microwave background and in the spectrum of primordial gravitational waves, and carefully teasing apart these signatures with future observational data promises to illuminate the physics of those extraordinarily ancient and consequential moments. In the final analysis, the ending of inflation set in motion the entire subsequent history of the universe, and understanding it would be among the most profound insights into our cosmic origins. The mystery of why anything exists at all. At the very foundation of all the questions we have gently wandered through tonight, beneath every puzzle about dark matter and distant galaxies and the nature of time and space, there rests the deepest and most beautifully unanswerable of all questions. Why does anything exist at all, rather than nothing? Philosophy and physics both approach this question with humility and wonder, and both find themselves ultimately at its edge, looking out into a silence that no current framework of human thought has yet been able to fill with a satisfying answer. Some theoretical approaches suggest that a universe emerging from nothing through a quantum fluctuation is somehow natural or inevitable, but this only pushes the question back further. Where do the laws of quantum mechanics come from, and why should they exist rather than not? This question, which a child might ask with perfect innocence and which the wisest physicists and philosophers hold with the same open, wondering hands, is perhaps the most peaceful of all mysteries, a question that requires not urgency or anxiety but only the same patient, resting curiosity with which you are listening to these words tonight, a quiet opening of the mind toward the vast, beautiful, and tenderly inexhaustible unknown. And so, dear listener, we come to the gentle end of our cosmic journey through 100 soft and wondering mysteries of the universe. Each of these vast and beautiful questions floats somewhere out in the deep, dark sky tonight, patient, unhurried, and eternally serene, much like the quiet that is now surrounding you. There is so much beauty in what we do not yet know, and there is so much peace in simply resting within that mystery. May your sleep be deep, your dreams be filled with the soft glow of distant stars, and may you wake tomorrow feeling wonderfully refreshed and at ease.